So good morning, everyone. Is this on? Okay. So this is the last lecture of the spring series. So the first thing is to let you all know we're still working on the fall, but we'll be in touch over the summer to tell you the details for the fall series. I want to thank all of you for both for coming to all the lectures in the series and also for your very generous support of the Compton lectures, which will really help us to continue them going as they've been. So thank you. I wanted to thank one other person, Mary, who has been here and has made everything work, including today remotely, is not here today. But I wanted to thank Mary for everything she's done. These lectures wouldn't go on without her. And finally, I want to thank Thomas for giving a really wonderful series on neutrinos. And I'm especially looking forward to today about future neutrino experiments. So thanks, everyone. I hope you have a nice summer.
All right, thanks so much, Ed. So as Ed mentioned, this is going to be the last lecture series, or the last lecture of the series, and I just wanted to kind of start by saying we've covered a lot of ground. So I know it's been a very dense series, a lot of material covered. You can read some of the topics that we've already talked about, and each one of these, I only kind of scratched the surface. There's so much more depth to be had in each one of these different things, but I hope to give kind of a good overview and hope to kind of synthesize it all in this lecture and talk about what we're doing to drive each one of these topics forward going into the next decade of neutrino science. So this is the last lecture, and we're going to start off with a little blast from the past. So going all the way back to where this lecture series began, we talked about how the decay of nuclei gave us the first hint that there was a neutrino, so that something was missing. So we have this spectrum here. This is the beta decay spectrum. And what this is showing you is that when a nuclei decays, it emits something called a beta particle, which we now know to be an electron. And you can measure the energy of those beta particles and draw what the distribution is of those energies. And you'll notice that it's continuous. It goes all the way down to 0 and all the way up to some endpoint value here. And this was the critical clue that told us that this decay had something else that we weren't seeing in it. And so this led to Pauli's famous letter in 1930, where he proposed the existence of an extra particle in the beta decay. And he called that the neutron. So I have hit upon a desperate remedy, he says, to save the exchange theorem of statistics and the law of conservation of energy, which wouldn't make sense if beta decay had this continuous energy distribution. So namely that there could exist in the nuclei electrically neutral particles that I'd wish to call the neutron. So going a little bit further, about 25 years later, we would actually discover this particle. So it had been renamed the neutrino, and two physicists, Frederick Reines and Clyde Cohen, built a clever club sandwich detector that was enabled to see this kind of neutrino interaction. So the idea was that the neutrino, you would put the detector by a very high energy, or not high energy, by a very high intensity neutrino source, like a nuclear reactor. And those neutrinos from the nuclear reactor would interact in the detector and produce a signal that you could see. And to make sure that it was a neutrino and not something else, they used the idea of this club sandwich, which had a collection of water targets and also scintillator. And the scintillator layers were used to amplify the signal. And when the neutrino interacted, you would get two signals that could be used to distinguish the neutrino from other things. So this is what they saw. They measured the neutrino interacting and producing a positron right immediately, and then a little bit later, the neutron from that interaction would be captured and produce a second burst of light. So it was this double coincidence using this technique that allowed them to discover the neutrino. So with the neutrino discovered, we started to look at how we could use that neutrino to make predictions about other phenomenon. And in particular, we looked at the sun and the sky. So we started to count neutrinos that were produced by the sun. We called these solar neutrinos. And then also we looked at neutrinos produced in the sky called atmospheric neutrinos. But something didn't add up. So this is a plot that we looked at in lecture 2, where this orange line is telling us the prediction, and then all these data points are showing years and years of collecting data from an experiment counting the number of argon atoms that were produced in a chemical reaction that a neutrino introduces, where it changes a chlorine atom into an argon atom. And you can see that the data is much far below, is further below the prediction. So this was the first hint. And this plot was really was driven forward by two physicists, John Bacall, who worked on the theory side of things, and then Ray Davis, who worked on the experimental side of things. Then the Super Kamiokande experiment and its predecessors started looking at atmospheric neutrinos, where we saw the same kind of thing. So atmospheric neutrino experiments measure neutrinos coming from all directions around the Earth, and you can make a measurement of how many neutrinos are missing as a function of that distance that those neutrinos travel. And this is what was seen by the Super Kamiokande experiment. In these hashed regions here, this is the prediction, and then the black data points show the data, and then the black line is fit to a new theory that was developed later as this data was being collected. And that theory we now know to be neutrino oscillations. So neutrino oscillations is one of the key characteristics of neutrinos that other particles don't have. So it's the idea that neutrinos change flavor as they travel. So the way this works is that neutrinos are a mixture of different neutrino masses. So when we talk about an electron neutrino, what we're really saying is it's an electron flavor neutrino, but it has different masses, and those masses can interfere with each other. By analogy, it's the same thing as rotating clocks or sine waves that overlap and form interference patterns. So each neutrino can be thought of as a combination of different clocks that are ticking at different frequencies. And when those clocks line up in particular configurations, they become one flavor or another flavor. In this case, I'm representing the electron neutrino here as a superposition of two of these mass neutrinos, so nu1 and nu2, but you can just think of these as the clocks inside the neutrino that are ticking as the neutrino travels. That causes the flavor to change. So using these ideas brings us to the present. So in the present, we take all of these puzzles that we had in the past. What's different about the beta decay spectrum? What are the issues with solar neutrinos and atmospheric neutrinos? And now we have this theory of neutrino oscillations that pulls it all together and kind of explains the phenomenon we see. And we can now use that to build tools for the present. So in particular, we're using the beta decay spectrum, like we talked about in lecture 5, to make measurements of the neutrino mass. So this is the picture of the Katrin experiment in Germany, where they're measuring very precisely this beta decay spectrum to look for signatures of missing energy in the electron that you could attribute to the neutrino mass. We're also looking at the sun for doing very useful physics that we could only do with neutrinos. So in particular, the Borax-Eno experiment shown here has made the world's most precise measurements of solar neutrinos that are coming straight from the sun's core. And combined with our understanding of neutrino oscillations, we can start to say something about the different fusion chains that are happening in the sun using these neutrinos. And then finally, atmospheric neutrinos really demonstrate the effect of neutrino oscillations, because with an atmospheric neutrino, the neutrino is coming from all directions. So you really get to probe all the different baselines and energies that are possible that could influence neutrino oscillations and build up a continuous picture of the neutrino oscillation theory using all distances that are possible. Also, understanding these neutrino oscillations has led us to design really interesting detectors to really narrow down and measure this effect. So we talked about in lecture 3 how we could build neutrino beamlines and neutrino reactor experiments to very precisely measure this effect. So in particular, we talked about the NOVA experiment, where a beam of neutrinos starts at Fermilab and then travels 500 miles through the Earth to Ash River, Minnesota, where there's a giant detector placed there. And then also, we can build neutrino detectors around nuclear reactors. So this is a photo of the double show experiment in France, which was one of the experiments that first observed oscillations from neutrinos produced at reactors. And then we just kept going. So we now have the Icarus detector operating at Fermilab, and then we have the Opera experiment that operated at Gran Sasso National Lab in Italy. And all of these different experiments have been used to say something about the way neutrinos oscillate, and their data are largely consistent with each other, which helps reinforce our picture of modern neutrino oscillations. We've also taken this idea when we understand neutrino oscillations very well on Earth and then applied it when we look out into space. So we've built really specialized detectors that are very good at seeing neutrinos with very high energies. So I've highlighted a couple here, so IceCube and the KM3net detector. And both of these work on the same principle of Shrenkov radiation, where a neutrino interacts and produces a high energy particle that travels through the detector incredibly fast and produces a big shock wave of light that is detected by light sensors inside the ice in the case of IceCube, or in the Mediterranean Sea in the case of KM3net. And combining these signals of high energy neutrinos with observations from telescopes and other astronomical observatories gives us a complete picture of what's happening out in outer space. But that brings me to the future. So we've accomplished a lot with neutrinos, but there's still a lot left to do. And in the past few lectures, I've started to talk about some of the remaining questions we have for neutrinos. These questions have become a lot deeper, and it's no longer just does the neutrino exist, but it's how does the neutrino act, how does it behave, and what are its properties. So in particular, one of the biggest ones is Dirac or Majorana. This was an idea that the neutrino mass is not quite like all the other particles in the standard model. It has this extra capability to act like its own antiparticle. And to understand that, we have to measure the neutrino's mass and understand the kind of interactions that neutrinos can undergo. We also have charge parity symmetry. This is another one that came up in the lecture on cosmology, where we talked about how matter and antimatter became imbalanced in the early universe. And that is related to this concept called charge parity symmetry, which neutrinos could exhibit. And we know that quarks do not exhibit at the right amount to explain the observed matter and antimatter asymmetry that we have today in the universe. In the previous lecture, we talked about if there are more than 3 neutrinos. So this is the idea of a sterile neutrino, where oscillations at short baselines have given us some hints as to that something might not quite add up when you look at short baselines. And then finally, just what else is out there. So we've only observed neutrinos from one supernova and only a handful of astrophysical neutrinos that have mapped back to known sources in the sky. So there's still a lot more to do and a lot more to learn from understanding what else is out there and waiting for the next supernova neutrino detectors to make an observation, for example. So with that, I want to get started with the last lecture. So I've titled it A Look Ahead. So it's all the things that we're looking forward to in the coming years. So I just want to start off with a little reminder about Cherenkov radiation. So this is a technique that has been tried and true in particle physics, and it's been used in a lot of neutrino experiments especially. So the idea here is that you have a charged particle traveling very fast through a medium, so for example, water. And if that particle is going faster than the speed of light in that medium, then it starts to emit radiation coherently along a specific angle. And so the picture here is showing that charged particle going through, and as it's traveling through, radiation is emitted, but only at particular angles. Does it coherently add up? And so there's this fundamental angle, theta c, that describes this. And when you build a detector filled with a medium and you have a neutrino interact in that detector, it produces these charged particles. And so in this diagram in the center, you have a neutrino interacting, and it's producing either an electron or a muon, depending on the flavor of the neutrino. And then it emits that Cherenkov light. And when you project that light at that specific angle along the path of the particle, and you instrument the walls of your detector, what you see are rings, because the light forms a cone. And so this is an actual event that was recorded in the Super Kamiokande detector, showing this principle really beautifully, where you have a neutrino interaction, and it produces probably an electron, and that light from that Cherenkov radiation emitted by that electron projected onto the walls allows the Super Kamiokande experiment to see these ring patterns very clearly and make precise measurements about neutrinos and their properties. So this, as I mentioned, this technique is tried and true, and really looking back on the whole lecture series, I want to talk about the Kamiokande physics program, because it's really been a series of detectors across several decades of doing neutrino research. So all the way back in the 80s, there was the Kamiokande experiment, the original, which was built not to study neutrinos, but to study proton decay. But then it turned out that they got involved in the solar neutrino problem and the atmospheric neutrino problem, and they became much better known for neutrino physics. And that all came to fruition when, in 1987, there was a supernova observation in the small Magellanic Cloud, not too far from the Milky Way, but close enough where we could see neutrinos from it. So then Kamiokande was eventually replaced by the Super Kamiokande experiment, which continued the legacy of Kamiokande and really made precision measurements of neutrino oscillations. So in 1998, they finally observed significant evidence of the atmospheric neutrino deficit and showed that it could be explained by neutrino oscillations. It was at this point that people were thinking about building these precise neutrino beam experiments. And, but also, unfortunately, for Super K, it had this accident in 2001, where while filling the detector, many of the PMTs imploded and caused a chain reaction, which slowed down progress. But the detector was rebuilt after that, and then it would go on to make lots of precision measurements in the coming years. The Kamiokande program has also been awarded 2 Nobel Prizes. So first in 2002 for Koshiba-san's observation of supernova 1987A and contributions to astrophysics through the solar neutrino observations from Kamiokande. And then finally in 2015, Kajita-san was awarded the Nobel Prize for the neutrino oscillation discovery. My story with the Kamiokande physics program started around 2018, where I joined, and then I was able to see the experiment through for the next couple of years throughout my graduate school career. So looking ahead, what's next for the Kamiokande program? I kind of gave it away, but it's the Hyper Kamiokande experiment. So after the Super K experiment, the idea is to go even bigger. So Hyper Kamiokande is the name of this experiment that's scheduled to turn on in 2027. And to give you a sense of the scale, it's not really possible to do in the pictures, but it's the largest artificial underground cavern ever constructed. It's 70 meters tall, roughly, and it's being excavated right now. So here are some photos of that excavation. This is the dome section of where the detector is going to go. And then you can see down here, these are just little tiny people standing in the middle of the dome. And then the excavation is still happening. So this is a photo from September of last year. They're I think they're over halfway down through the cavern excavation. And so why build bigger? The answer is more data faster. So just to make a little comparison of the different detector sizes, so Kamiokande is represented here, this tiny cylinder, and that took data for a few years. And then finally Super K turned on, which increased the size tenfold. And then that has been taking data continuously, and then around 2027, when Hyper K is scheduled to turn on, we'll have something that's even larger, so about an 8-fold increase. And so you can imagine, just if you turn this purple box on its side, it fits nicely within the first year of Hyper Kamiokande data taking. So in a few years of Hyper Kamiokande data, we'll have a Super K equivalent of 20 years of data, right? So this will really accelerate our ability to understand neutrino physics. Super K, as part of its history, has been part of the long baseline experiment, the Tokai to Kamioka experiment. And the idea here is to make precision measurements of neutrino oscillations. And the way this works is that you have a neutrino beam at the J-Park facility on the east coast of Japan. It travels through some near detectors which characterize the flux of neutrinos that are going across Japan. And then on the west coast is Super Kamiokande. And so the idea now is to upgrade this whole baseline. Hyper Kamiokande will be very close to where the existing Super Kamiokande cavern is, and then an upgraded beam facility at J-Park plus upgraded near detectors will enable very precise measurements of neutrino oscillations at a much faster rate in the coming years. So the main physics goal of Hyper Kamiokande is CP violation. And so this is this idea, do neutrinos and antineutrinos oscillate differently? And to give you a kind of sense of how that might look in the Hyper Kamiokande experiment, I have these two plots. So on the vertical axis here, this is the number of muon neutrino events that have oscillated into electron neutrinos. And that, we think, is our best probe of CP violation. And you can look at the same thing in the antineutrinos. So you can change your beam from a neutrino beam to an antineutrino beam. And if charge parity is not conserved, then you should see these things move in opposite directions. So in other words, the number of electron neutrino events due to this oscillation effect should increase in the neutrino beam and decrease in the antineutrino beam. And to give a sense of scale for this, in about 10 years, Hyper K expects to have over 1,000 events of each of these different configurations. So 1,000 of muon neutrinos oscillating to electron neutrinos and 1,000 anti-muon neutrinos oscillating to 1,000 anti-electron neutrinos. And to compare that with 10 years of T2K running, they only found about 120 of these things. So the statistics will just be enormous, about almost a factor of 10 better. So next I want to go back to a different detection technique, the liquid argon time projection chamber. And this is something we talked about in the previous lecture in the context of the SBN program that's now happening at Fermilab. So after my graduate school career, I joined the SBND experiment, and just in time for it to start taking data last year. And this is a picture of what it looked like as it was being lowered into the cryostat where the liquid argon goes around this detector. And the way this works is that you have these planes of wires that are very finely spaced, and those wires detect the charge instead of the light produced by the particles, like in a Shrenkov detector. You're actually producing images of the charge that's deposited by those particles as they go through the detector. So you get these very high resolution images, and this is a picture of a neutrino interaction from SBND that was taken last summer, or recorded last summer, where you have a neutrino that's coming in. It actually doesn't have any charge, so it makes no track, but then you have a big spray of particles coming out on the other side. And you can image those things to get a very precise idea of what the neutrino energy was, and you can count up all the different types of particles that are in these interactions. So this is a future technology that is being actively developed. And we saw last time how this technology is being used by the SBN program at Fermilab to answer this question about oscillations at short baseline. So I showed this figure last time where that one of the anomalies that we've been investigating is if there is an excess of electron neutrinos at low energy that show up due to possibly a sterile neutrino. And the microBoolean experiment, which completed its data taking run a few years ago, but has just recently released its analysis of the data, was shown here, and they conclusively said that there was no excess in the electron neutrinos that could explain the mini-boon excess that was one of the hints that we had about this phenomenon. So there's still more to do on that, and the SBN program is still has a lot of work to do to actually identify the source of the mini-boon excess and also investigate other anomalies. But in general, the liquid argon time projection chamber technology is ready to be used for new physics. So for other physical or other neutrino physics topics beyond just the short baseline program at Fermilab. So in particular, the precision oscillation area, just like the Hyper-K experiment, but then also solar neutrinos, supernova neutrinos, and atmospheric neutrinos have never been looked at with a liquid argon time projection chamber before. So we can use the same technology to revisit some of the areas of physics that we have previously used to great effect to gain understanding about our universe. And the flagship experiment for all of this is the DUNE experiment, the Deep Underground Neutrino Experiment, which will be hosted here in the United States. So the idea is that you take a very powerful neutrino beam that's produced at Fermilab. You have a series of near detectors, just like in the Hyper-K or the T2K experiments, and you have that beam travel through the Earth a far distance, about 1,300 kilometers, to a deep underground laboratory. And the reason you put it deep underground is so that you can get rid of all of these different backgrounds from cosmic radiation that might be present if your detector is too close to the surface. And that enables a rich program of not only neutrino oscillation physics, but also these other things, solar neutrinos and supernova neutrinos and so on. So just some photos of this. At the far site, which is what we call it in South Dakota, there's going to be a cavern here where two giant liquid argon time projection chambers are placed. And so here's a diagram of that. And then at Fermilab, there's going to be a new linear accelerator that's going to produce the protons that are required to make a very high intensity neutrino beam. And that's being constructed now. And here's an artistic rendering of what that might look like. On the Fermilab campus, there's going to be this new area where this linear accelerator is going to be housed. In the meantime, we're also preparing for building the detector experiments in many ways. So one of those is the Proto-DUNE experiment at CERN. This is a photo of what that experiment looks like and the size it takes up. But the thing to remember is that this is just 1/20th of the size of the DUNE experiment. So one DUNE detector will be 20 times the size of this one, which is already quite large. And the idea here is to do research and development for building and installing and data taking and designing the systems that will be used in the DUNE experiment. So inside the detector, here's what it looks like before the wires for the time projection chamber are installed. DUNE is making really good progress, actually. So in February of last year, the DUNE caverns were fully excavated. So this is a photo looking down one of those DUNE caverns in South Dakota in this mine, deep underground. There's actually 3 of these caverns, so this is only one of them. And the detector installation will be following shortly. So what does DUNE hope to do? So DUNE, just like Hyper-K, is going to make precision measurements of neutrino oscillations. Actually, based on DUNE's geometry, it thinks the DUNE collaboration believes that within 3 years of data taking about, they can answer this question about which ordering of neutrino masses we have. So we've talked about this in previous lectures, but there are 2 cases that we can have for neutrinos, and it's very hard to disentangle them with oscillations. But DUNE will have so many statistics that they think they can do it. So the idea is that either we have a universe called the normal ordering, where the neutrino masses are 1 heavy neutrino masses and 2 light neutrino masses, or we could be in a universe with the inverted ordering, where there are 2 heavy neutrinos and 1 light neutrino. So either of these things are possible, and DUNE hopes to be able to distinguish them. And then just like Hyper-K, you have the measurement of this CP violation, so charge parity violation. So here's a simulation of what it might look like in the DUNE detector after a few years of running. So within 5 to 10 years, DUNE hopes to be able to see CP violation or confirm CP violation, depending on how much of it the neutrinos actually exhibit. So here's an example of what that might look like. The DUNE data where charge parity is a conserved quantity follows this line, but then if it's maximum, then you would see an enhancement to the rate of muon neutrinos oscillating to electron neutrinos. And then, as I mentioned before, the DUNE program doesn't just stop here. It's revisiting all of these other topics that I mentioned with the liquid argon time projection chamber technology. I just want to show one other highlight about DUNE, which is that DUNE is actually happening here at University of Chicago. So to build the wire planes that are required for the DUNE experiment, it's a worldwide effort happening both here and in the UK. And Ed Blucher is in charge of managing this program. So actually, a couple blocks from here, we have these machines that wind the wires around a frame to then go into the DUNE experiment. So one DUNE module will need about 150 of these, and so it helps to have a robot to do it for you, to wind the wires around. So you can see a video of what that looks like. The question was, is this at the accelerator building? No, this is actually at a new building called the High Bay, which is, it's on 56th. Yeah. Okay, so switching topics a little bit. So these are precision oscillation experiments. I want to talk about the other types of detectors that we've mentioned in this series. So specifically ones that use inverse beta decay as their detection mechanism. So we've seen this before. This is the same technique that was used by Reines and Cohen for the first detection of the neutrino, and it's still going strong in helping us build better and better neutrino detectors. So the idea here is that you have an anti-electron neutrino and it interacts with a proton. When that happens, you have the proton change into a neutron, and a positron, or a positively charged electron, is emitted. So when that positively charged electron is emitted, you get a prompt signal of light. You get light in your detector right away, and then that neutron bounces around for a little bit. And after a while, that neutron bouncing around, it eventually meets up with a proton and emits a second burst of light. And it's that coincidence between the first and second burst of light that tells you it was an anti-electron neutrino interaction. And so just as a reminder, this is kind of what it looked like in the Reines and Cohen experiment, where you had the prompt positron first, and then a little while later, a delayed neutron signal. And by looking for these pairs, you can say something about how many anti-electron neutrinos interacted. So we've seen a couple detectors throughout this series that use this technique, that use liquid scintillator specifically to make the measurements of this process. So we looked at the Camland experiment in lecture 3, which was looking at the oscillation of neutrinos from reactors all across Japan. And then we also looked at the Diabae experiment, which was looking at oscillations from reactors that were much closer by, about 1 kilometer away. And both of these experiments kind of follow the same pattern. They have a big tank of liquid scintillator that's viewed by photomultiplier tubes to detect the light from both of those, from the positron and also the neutron capture. And then they try to get as low backgrounds as possible because the energies of the neutrinos that they're looking for are in the MeV range, the mega electron volt range, which is much lower than what you would have in a neutrino beam, for example. So in particular, the Diabae experiment has this tank of water around it that helps to reduce the amount of backgrounds that it experiences. So anyway, the culmination of these techniques has led us to a really phenomenal experiment called JUNO, the Jiangmen Underground Neutrino Observatory. And here's a photo of what it looked like just a few months ago. It's being constructed now. And it's the same idea where you have a big tank of liquid scintillator and then inside or around it will be a big tank of water to reduce some of those backgrounds. So just to give you kind of a scale of the experiment, it's about 20 meters across, and it's all filled with liquid scintillator, and then around it is a very dense packing of these photomultiplier tubes to try to get as much light from the scintillator as possible, so you don't miss any of the energy that's deposited in the experiment. So there are about 20,000 photomultiplier tubes for 20 kilotons of liquid scintillator. And just as a point of comparison, Super Kamiokande has about half as many phototubes and twice as much volume. So the packing of the phototubes in the JUNO experiment is really a lot denser than what we've had in other detectors so far. So JUNO also has a pretty broad research program, a lot of different topics in neutrino physics. So their main one is actually neutrino oscillations using reactors as the source instead of a neutrino beam. But they also plan to do supernova neutrinos, solar neutrinos, and then the one I want to talk about, which we haven't mentioned in this course so far, is actually geoneutrinos, which I think is really exciting. So the idea here is that one of the questions in geology is how much heat does the Earth produce from the mantle versus the crust? And we actually don't know the answer very well because there aren't that many probes that we can do of the material in the mantle of the Earth. And so one idea is to actually use the emission of neutrinos from the mantle and try to measure that heat by proxy of neutrinos. And so this is a very difficult signal to look at. You need a detector that can see very low energy antineutrinos coming from the decays of uranium and thorium in the mantle of the Earth's crust. So actually the Juno experiment expects to be able to see an appreciable number of these. So this is a figure showing the antineutrino spectrum that they expect to have. And you can see in this black line, this is the antineutrinos from reactors. And if you have enough energy resolution, then you can actually start to see the wiggles due to oscillations on this spectrum. But you'll notice that at the very lowest energies, there's also a big contribution here from geoneutrinos. So actually, the Juno experiment might be able to say something about the heat coming from the mantle using this effect, using how many geoneutrinos they see at the lowest end of their energy spectrum. So that's a really exciting development that could happen. One other thing I want to talk about with reactor neutrinos is this idea of reactor monitoring. So using neutrinos as a way to enforce treaties for nuclear nonproliferation is a really interesting idea for how neutrinos can be used as part of society. So this has a lot of advantages because neutrinos can't be shielded. So in other words, if you build a nuclear facility, then there's no way to block the neutrinos from it or hide the neutrinos from it. You have to have, or neutrinos will be produced and they can't be shielded by anything. So there are a couple ways you could go about doing this. You could think about building something that we would call near-field monitoring, where you have a nuclear reactor core and you place a detector nearby, and then you can ask questions like, does the reactor's fuel consumption match what it's reported to be or what it's proposed to be? So you could build a detector that could sit very close to the core and then over a couple weeks or months would be able to tell something or say something about the fuel cycle in that reactor based on the flux of antineutrinos coming from the reactor. Also, monitoring nuclear waste could also be done using the same technique, same idea. And there have been different proposed detectors for this. There are some operating detectors that are operating at research reactors and trying to make measurements of the flux of antineutrinos from them very precisely so that you could say something about the reactor fuel cycle or the reactor power and see how long it would take to actually get that signal. There's also some other interesting ideas, so like a mobile neutrino detector that you could put on a trailer and drive around to different sites that are in question for nuclear security purposes. There's also another idea called far-field monitoring, where you have a big detector like Super Kamiokande size, for example, where you don't necessarily know where the nuclear facility could be, but you have a detector that's able to look at the flux of antineutrinos coming from all reactors and maybe say something if there are too many antineutrinos or too few, and then what would that tell you about the presence of nuclear activity within a certain radius around that detector. So I'll just highlight one of these approaches. This is the SNO Plus experiment, which is a phased multi-purpose neutrino observatory built where the SNO detector was. So the SNO experiment was instrumental in determining solar neutrino oscillations back in the early 2000s. It has been succeeded by the SNO Plus experiment. And the way this experiment works, it's in phases. So the detector is filled with different substances, and then neutrino interactions are measured during each one of those phases. So it started with a pure water phase for a couple of years, and then finally that water was replaced slowly with liquid scintillator, which is now running now. And then the plan is to eventually add tellurium to the water. I won't talk about why, that's a topic for another day. But it's been a really successful physics program. And one of the exciting things about SNO is that it's very low background. And so low background, in fact, that during its pure water run, it was able to measure neutrinos from nuclear reactors consistent with the flux of neutrinos expected from all the reactors in Canada and then also the United States. So this is a plot from their publication just in 2023. The number of anti-electron neutrino events recorded, and then in red here is the expected contribution from the reactors across the United States and Canada. And so the data actually follows the prediction pretty well here. And so this was the first demonstration of using a water detector to see neutrinos from nuclear reactors. And this is exciting because water detectors are pretty easy to deploy, relatively speaking. SNO Plus has a lot more fancy features, but if you were to build a neutrino detector to do reactor monitoring, you'd want to use a water detector because it's simpler to construct and then also to make it very large too. So that's in contrast to a liquid scintillator detector where it takes a lot more management to successfully operate a liquid scintillator detector. Okay, so switching to another topic that we've talked about is astrophysical neutrinos. We're also making great strides in improving our understanding of neutrinos that come from the universe beyond our galaxy. So these are the highest energy particles we could ever hope to observe on Earth. And the reason for that is because they get accelerated in these cosmic accelerators like active galactic nuclei, or AGNs, where the strong magnetic fields are moving particles around very close to the speed of light, and those particles interact with the dust or the other medium around those galaxies and produce neutrinos that then make their way towards us. And in contrast to other particles that are produced in these active galactic nuclei, the neutrinos are undeflected, so they don't scatter as they travel from the source to the Earth. And so when they arrive at the Earth, we have a chance of detecting them if there are enough of them, and their energies will be very close to what they were when they were produced. So that's a very exciting way to look into the universe, and we've already demonstrated through the IceCube experiment that we can match these neutrino observations with measurements from telescopes. So in particular, gamma ray telescopes. This is an image of a neutrino that was detected in the IceCube experiment, matched with the heat map of gamma ray sources in the galaxy, and you can see that the neutrino points directly back to this source with very high resolution. And so this is great, but there's a lot more to do with these astrophysical neutrinos. So we don't really know where they come from. We have a couple examples where we think they're very likely candidates, but we don't have a good statistical sample of the different kinds of sources that they can come from. We also don't know the mechanism that accelerates them. So by making a catalog of the different sources where these neutrinos come from, we can hope to say something about the types of mechanisms that must be present to create these high-energy neutrinos. And then finally is just a very fundamental question, but our experiments on Earth only go up to a pretty small energy compared to the energies of these neutrinos. So it's also a great test of our understanding of particle physics extended to the highest energies, because we could never hope to recreate those energies at a particle collider. They're orders and orders of magnitude higher than what we currently are able to achieve. So really, these neutrinos would be the final frontier of particle physics. And so to go after them, we're building extensions and upgrades to our existing experiments. So this is a artistic rendering of the IceCube Gen 2 concept, which is scheduled to be installed in the mid-2030s. So the idea is to take the existing IceCube detector, which is shown here, and then add many, many other strings in the Antarctic ice with more sensors to expand the volume and also the energy possible to record in this experiment. So here's a map, top-down view of what this looks like. So the existing IceCube experiment is here in blue, and then the proposed strings, or the planned strings, are shown here in orange. And so you would have a dense core. I mean, IceCube is not really dense. Each one of these blue strings is about 100 meters apart. But then instrumenting the Antarctic ice even further for about a 6-kilometer cubed volume, something like this. And what you get when you do this is a map of the sky that could produce hot spots that you could see. So you could really pinpoint where the sources of neutrinos are when you look up into the sky using this detector. So this is a map of the sky, and then simulated what it would look like if you had neutrino sources kind of distributed uniformly across the sky, what the IceCube Gen 2 experiment would see. It would see with very high confidence neutrinos coming from very narrow regions of the sky. And that would be great to help us build up this catalog of the sources that produce these high-energy neutrinos. Another exciting thing we have going on is that we're building not just bigger neutrino telescopes, but more neutrino telescopes. So we've talked earlier in the series about the KM3 experiment, which is a similar concept to IceCube in the Mediterranean Sea. They've recently recorded the highest energy neutrino ever observed, and that was done with about 1/6 of the planned full detector size. So in its full realization, the KM3 detector would actually look like this, with over 200 strings. And as I mentioned, there are only about 33 that are currently installed. So the KM3 experiment, just like the IceCube Gen 2 experiment, is expected to get larger in the coming years. But then also there are other experiments like the P1 experiment, which is proposed to happen just off the coast of Canada and the United States here in the Pacific. Same idea, you have these strings of light sensors suspended from the ocean floor that could detect these high energy neutrinos. And when you have this worldwide network of neutrino detectors that are all capable of seeing high energy neutrinos, you can make a map that looks like this, where each band shown here is kind of the expected best or favorable range of each neutrino telescope. And you can see by putting the neutrino telescopes all across the world, so in the South Pole, the Mediterranean Sea, the Pacific Ocean, you get a nice overlap of where each of these experiments are expected to see signals. And you can start to cover the entire sky with neutrino detectors that are very sensitive to these high energy sources. And so you can start to look at correlations between the experiments, but also have some experiments that could see a signal where others would not have coverage. Okay, one more topic that I want to talk about the future of, which is neutrino mass and double beta decay. So this is something that goes all the way back to how the neutrino was originally discovered, so with the Reines and Cohen experiment, where they were looking at neutrinos that came from a beta decay process, so in a nuclear reactor. We've now gotten to the point where we can take specific elements and look at the beta decay spectrum of those and measure those incredibly precisely. So in particular, tritium has been used in a lot of experiments that want to very precisely measure the spectrum of beta decays. And the way this works is that you have a beta decaying element, and it has some distribution of energies for the electron that's coming out of that beta decay. And this enables you to measure the neutrino mass by looking just at the endpoint here. So in lecture 5, we talked about how you could take the beta decay spectrum and look and zoom in very close to the endpoint. And if the neutrino has mass, which we know it does from oscillations, you should be able to see a little bit of a deflection of that endpoint due to the energy that goes into the neutrino mass, separate from the energy of the electron. So you should be able to see kind of a distortion of the endpoint of this spectrum. And that's the idea of the Katrin experiment in Germany. They're currently the world's leader in making this measurement of neutrino mass and really zeroing in on this endpoint. And the current limits that they've set are around 500 millielectron volts, or 0.5 electron volts for the neutrino mass. Closely related is the idea of a double beta decay. So this is the Katrin experiment is looking at single beta decays, but to get at the concept of how neutrinos get mass and understanding the properties of the neutrino, you can also look at double beta decays. So particular elements will undergo a double beta decay process where you have 2 neutrinos emitted and 2 electrons emitted, and you can similarly ask what's the spectrum of that decay process. And if the neutrino is its own antiparticle, which is an open question, then some of the time you should be able to have those neutrinos cancel out in the decay, and the electrons emitted with the full energy of the decay and act like a single energy point at the very end of this spectrum. And this is the idea that's being looked for in a lot of experiments worldwide, but in particular, I'm showing here the Legend 200 experiment, which is one of the world leaders in making this measurement. So the same idea, you have this spectrum of energies from the electrons that are coming from these decays, and you zoom in on the endpoint here. And for the double beta decay experiments, they're hoping to see a little bump just at the end. Okay, so there are 2 ideas for improving this going forward. So Katrin has kind of reached the maximum size you can build it to very precisely measure these electrons. So what if there was a new technique that could get even better precision on the electron without having to go even bigger than Katrin? So this is the idea of the Project 8 experiment, where, just like I mentioned before, they take tritium just like Katrin, and that decays via beta decay. The nuclei it becomes after the decay is helium-3, and an anti-electron neutrino is emitted, and then also an electron. And Katrin is trying to very precisely measure this electron, which comes out at different energies from the decay. The Project 8 idea is to instead put the tritium in a magnetic field so that when it decays, the electron actually follows the magnetic field line and starts to spin around that magnetic field line. So here's a picture of you apply a magnetic field. That electron no longer just flies out in a random direction. It starts to stick to the magnetic field lines and starts to spin around. As it's spinning, it emits radiation. And so if you have a carefully placed antenna, you can start to detect that energy or that radiation from the electron as it's spinning around. And you could make a very precise measurement of what the electron's energy is by recording the energy of the emitted radiation as it spins around these lines. And this has a lot of advantages because Katrin, I'll just go back for a second to show the photo here. So Katrin, this whole giant thing that's moving through this German town is built to move the electron very efficiently from one end of the detector where the tritium is to the other end where it can be precisely measured, its energy. But if you have Project 8, where you have the tritium already in a magnetic field and you're just putting an antenna next to it, then you don't have to move the electron at all. So it has a lot better statistical power. You don't have any losses from the electrons in this way. And so it can be very effective to go even to get more data than Katrin has. So this has been demonstrated. Here's a little picture of the setup from a prototype of the Project 8 experiment. And then this is a plot showing the readout of that frequency measurement. So on the vertical axis here, this is the frequency, and then the horizontal axis is time. And when one of these electrons is emitted, what you see is that the frequency goes up as the electron starts to lose energy. It starts to spiral faster and faster. And then sometimes, if the vacuum in the experiment isn't perfect, that electron will hit something, some impurity in the gas, and it will lose energy very quickly. So it scatters down in energy also, so that you have some discrete steps in this spectrum. But really what you're trying to measure is the energy of the electron. So just by seeing kind of this pattern, you can very precisely calculate what the energy of the electron must have been at the time it was emitted. So this technique works, and the expectation is that Katrin, after it's finished running, will have a resolution on the neutrino mass of about 0.2 electron volts, but Project 8 is expected to get about an order of magnitude better, so 0.05 electron volts, to really zero in on the neutrino mass and hope to make a measurement of it. Okay, so finally, neutrinoless double beta decay. It's also getting bigger. One idea is to take the legend concept and just expand it and also reduce the backgrounds. So this is the idea of the Legend 1000 experiment, which is not built yet, but it's the successor of the Legend 200 experiment, instrumenting about 1,000 kilograms of high purity germanium to look for these neutrinoless double beta decay events. And if the background can be reduced sufficiently to the point of expecting one background event per every 10 years of running, then you could hope to probe lifetimes of the neutrinoless double beta decay process of about 10 to the 28 years. So much longer than the age of the universe, right? But it would give us a really great chance of seeing this process if it exists. And what that data might look like is shown down here. So on the vertical axis here, you have the number of events, and then on the horizontal axis is the energy. And one nice thing about these germanium detectors is that the energy resolution is incredibly good. So each one of these bins is very narrow, which means that you can localize the energy of that event very exactly, very precisely. And so you have some background from double beta decays where the neutrino does not annihilate each other before the interaction happens, and so that kind of forms a tail. And then you have some backgrounds from maybe from radiogenic sources. But then on top of that background, you would expect to see an event or an excess of events at a very particular and very narrow energy range, which you could attribute to neutrinoless double beta decay. And so, in other words, the probability of having background events kind of line up in the same energy bin when the energy bins are this narrow is almost zero. So you could really make a discovery with this kind of experiment. And so the detector concept is shown here, where you have different volumes of instrumented detectors, each containing multiple hundreds of kilograms of germanium. You put it underground, and you put a lot of shielding around it to try to reduce as many of those radio backgrounds as possible. So in the next couple of years, we hope to have answers to a lot of these questions. It's going to be a pretty busy decade, I would say. Like, we have a lot of homework to do still, but we have detectors and we have ideas that are being planned and being built that will help us answer a lot of these questions. So just a few I've listed here. There are definitely a lot more, but check back in 10 years for the next Compton lecture on neutrinos, and maybe some of these will be answered. So with that, I'd like to thank you all so much for coming. I've learned a lot from all of your questions, and this has been a really great experience for me, just in terms of learning how to communicate everything on all these different ideas, and your questions have really helped drive that forward. So thank you so much for your attention.